Thank you. So good morning. So thank you very much for coming. So today I will explain how to solve the initial value problem of box-ball system I introduced yesterday. So let's recall something I told yesterday. So let's recall. So I introduced discrete KDV and discrete Toda lattice. And so, yesterday I introduced their network description. And which will be very good to tropicalize, to have, please recall that we have sign coherence in the coefficients of spectral curve. Actually, it is very it works very well in tropicalization, and we can keep some information for box-ball system, so which is related to discrete KDV. Tropicalization, we get so box-ball system, as I mentioned briefly in the last part yesterday. So actually, discrete Toda also related to box-ball system in a little different way, but I don't talk about it. But actually, both are very important to consider the symmetry of box-ball system actually. So today, I consider the linearization of the time evolution of box-ball system by using a very combinatorial way. So before that, I'd like to make a brief remark on tropicalization. So in general, so I talk about general setting from the first time. So let K being an algebraic closed field. Like Puiseux series in mind. So Puiseux series in T, for example. And so T is different from the time coordinate I used here. So this is a variation field. So which is a map from K minus 0 to real numbers, satisfying the following property. So valuation of A times B in this field is the summation of each valuation. And this is easy to understand. The next one is important, valuation of A plus B. And this is equals or bigger than the minimum of valuation of each valuation A and valuation B. So there is an inequality here. And for example, in the case of Puiseux series, so valuation of, say, A times T to N like this, so say A is in is a complex number, and N is some rational number, for example, then its valuation is N. So by using this thing, we can calculate the valuation of a given element in K. Then further, I define tropicalization of, so it will be a tropicalization of a spectral curve. So let F be a polynomial in X and Y whose coefficient is in K, like this, FAB, which reminds you of yesterday's spectral curve. So like this, then it is in this polynomial ring. And we define a tropicalization of F as the following minimum plus polynomial as a valuation of this f plus and a times y and plus b times x. So this is the definition of tropicalization of this polynomial in x and y. So I will use this later. And I'd remark that so the relation with sign coherence. So let ui be an element in K, and whose variation is capital UI. So I use this small u to the dependent variables of the discrete KDB, and this is for the boxable system later. And so if some Lola monomial, monomials in K Lola monomials in these variables in the UI. Let's consider this one and assume that these two have the same sign, plus or minus is the same sign. Then valuation of F1 plus F2, is equal to the minimum of valuation of F1 and F2. So in this case, that inequality becomes equality in this specific case. So, excuse me? Yes, right. Coefficient in, this is a monomial, so how to say, it was not very, accurate. But so let F1 and F2 are the Lola monomials in the UI, whose coefficient is in C, for example. We consider such a situation, and we assume that the sign of these things are the same. Yes, right. So that inequality appears when the minimum term in, for example, in Puiseux series may vanish in this plus if the sign is different, but we don't like such a situation. So please note this very basic property. So it, yes, right. And so it is related, so how to say, the boundary is related to the Newton polygon. Yeah. So then I will use this property later. And so yesterday I introduced the relation between discrete KDB and so periodic boxable system. So the relation was given, so if you assume a valuation of boxable system, the dependent variables of a boxable system, UTK is capital UTK. So then for some parameter delta, its variation is 1. We assume such a condition, and we assume that in the infinite boxable system with infinite carrier, we assume that if the coordinate k goes to plus minus infinity, then it should be 1 at the far boundary for infinite boxable system. And for periodic boxable system, we assume that usual periodicity L, then we get periodic boxable system in this variation by taking the variation appropriately. So it's very rough statement, but I'd like to say that some tropical limit by using that valuation, we get both boxable system and periodic boxable system from a discrete KDB, depending on the boundary condition. Yeah, they are different. I'm sorry. yeah. So okay, so then next I'd like to switch to solve the initial value problem of the periodic boxable system. So for that, I introduce Kerloff-Kirchhoff reciprocal correspondence. So it's two wrong names, so I write it KKR for short. So today I only use the case of affine A type. So in general, it is defined, this map is defined for A and I, so affine SL n+1 case. So let's consider set BL. Now L is not always the period for periodic boxable system. So L is a set of 1 and 2. The tensor product is L, so this set. And we assume that we fix some M. It is from 1 to half of L. Then we define a subset BLM, which is so sequence of 1 over 2, whose length is L, like this. And this M gives the following condition. So number of 2 in this B is exactly M. This is such a subset. Then I further define the subset of this one. So BLM plus, it means that the sequence B in this BLM, such that number of 1 in this sequence up to K from the left is always bigger than the number of 2 in B in the sequence of the same length from the left for all K from 1 to L. So you count the number of 1 and K from the left, and it says that always the number of 1 is not less than the number of 2. So this is called the set of highest path. Then this set is the basic things from now. And further, I define the set RLM. This is a little bit complicated set. So this is a pair of partition lambda and some tuple of positive integers R. So here, lambda is a partition like this. Say the length is G, and this is a partition of M. So we have M here. So, and R, for this partition lambda, we define R as a sequence of G positive integers. So non-negative integers, sorry. And such that I write several complicated conditions for R from now. For lambda, R is given. And for lambda, we define a positive, non-negative numbers P from now. And each R is required to be reduced to between 0 and Pi. And Pi is, I'm sorry, it is very complicated, L minus 2 times the summation of the minimum of lambda I and lambda K. And here, I is fixed, and the K is from 1 to G. Then, please recall that we assume this condition, so it is not negative. I will show an example soon. So then this number is called vacancy number. And this R, this one, is called a rigging for lambda. This R. So for this, we have a partition, and it's rigging, satisfying this condition. So like this. Then there is a theorem by Kirov-Listikin as follows. This is KKR correspondence as follows. So there is a one-to-one correspondence between BLM plus and this set of a set of pairs of partition and rigging. So this is a theorem. And let phi be a map from left to the right. So I've forgotten to say that the pair of lambda and R, so lambda, this is called a linked configuration. So it is called rigging. It is a kind of decorated partition. Then the algorithm of this correspondence is very, very complicated actually, but to understand the linearization of box-ball system, we cannot avoid this totally. So I'd like to show only one example from now, how to calculate phi by taking a small example. So let's consider the case that L is 8 and M is 3, for example. So we consider 1, 1, 1, 2, 2, 1, 2, 1. It is an element in B8, 3 plus. You can see that the number of 1 and 2 satisfy this condition. So by cutting this sequence from the left, one by one. Then first, we start with empty partition. And we go from left to the right by keep picking up these numbers one by one. Then if when we pick up 1, nothing occurs. So we start with empty one, and we pick up 3, 1. And we have to memorize that we picked up 3 numbers. So we denote it as by using this notation. Then next, we meet first 2. Then something non-trivial occurs. So first, we memorize that we picked up 4 numbers. And corresponding these 2, we draw 1 box here. And next, we calculate this P for this partition of 1. So here, L is 8, and we have only this one. L is 4. I'm sorry. In this case, we looked at the number of numbers we picked up. So this is 4. So now L is 4. The 4 minus 2 times this one. And now we only have 1 box. So it is, P1 is 4 minus 2 times 1. So we have 2. So we write 2 here. And and also we write 2 in the left-hand side too. Then next, I pick up 2 again. And now we picked up 5 numbers. And so we draw 1 more box. So we add a box to this partition. And the way is as follows. So although it is trivial now, but if this box has the same number in both sides, then we can add a new box to the same row as this. So it is a case. And so next, I calculate P1 to this partition with L is 5. So now P1 is 5 minus, 2 times this size of box. So 2 times 2 now, so it is 1. So we write 1 here and also here. Then next, we meet 1 here. So we have 6 numbers. And because it is 1, so we don't add any box here. And so we just keep the right number, 1 here. And we calculate P1 for this configuration. And now this part is changed to 6. So now we have 2 as P1. So in the left-hand side of box, we write P. But in the right-hand side, we write rigging. So it will be rigging. And at this point, these 2 numbers are different. Then, next, I add 2. Maybe I change here, the 2. Then we have now 7 numbers. And so when we added this 2, it was added to the same row as before. But this case is different. So this case, the difference is that the numbers, right and left numbers are different. So in such a case, we have to create a new row like this. Yeah, it's very complicated rule, actually. This just memorize the sequence P. So yes, P, this one. And in the right-hand side, we have rigging R, and it should satisfy this condition. So when a new box is added, the rigging of that row should be the same as P. This is a rule. But if, so we write 2, 2. This is a P and R. So 2, 2, and 1, 1 when a new box is added. But for example, in the case as this, we calculate P, but we don't change the rigging. And we don't add any box to this row at this step because we had 1. When we have 2, we add a new box to the partition by following the rule that if there is some row which has the same rigging as P, then we can add a new box to the same row. But if the number rigging and P are different like this, we have to create a new row. So R? No. Yes, right. Yes. So only one row here, up to this. So this is P, and this is R. Yeah. So yeah, I'm sorry, it is always confusing. So yeah, P and R. So now, something different occurs here. So now we create a new row here by adding this 2. And so we now calculate P1 and P2 for this partition by using L is 7. So in this case, we have for P1, we have 7 minus that this formula means that we just count the number of boxes less than this line. So we have 3 boxes here. So we have 6 now. So it is 1 here. So it's just a coincidence in this case that we have the same numbers as P and R. And so for the second row, we have P2. It is 7 minus 2 times 2 now. So we just count the number of boxes to the left of this line. And this is 3. So we write 3 here and also 3 here because this box is newly added this time. So finally, we can finish here, but for consistency, I finish it by adding the last one. So we have 8 numbers, and the partition isn't changed, and the rigging is also not changed, but this P are changed to 2 and 4 because this part 7 is now replaced with 8. So, but finally, we can calculate the image of phi. So phi of this B is partition 2, 1, and this rigging 1, 3. So this is a calculation. Yeah. Yes. Right. Yes. So yeah. So it's I know that also for me it was terrible to understand this rule for the first time. So if you add 1, partition isn't changed, and so only P is changed depending on the information of the previous partition and the number of these integers we picked up. And if we have 2, then we add a box depending on some rule, as I explained. Yeah, so okay. So maybe it is understandable to consider this or this case. So for this case, we have the same rigging as P in this row. In general, we have many rows as this, for example, and there is some P1, P2, P3 here, and we have R1, R2, R3 as the intermediate state of the calculation. And if some R2, so for example, R2 is same as P2, then we can add a box to this row. So if you have several rows where R and P are the same, then you can choose any one of them in general. So always, if you can put a box in the existed row only when P and R is coincide. Mm-hmm. Yeah, you can choose anything. Yeah, but actually, so if such a thing occurs, the number of columns should be the same actually. So you can choose any of them. So yeah, but it doesn't matter. You can change the order of row always after calculation. So it doesn't matter actually. Then if all rows all R are different from P, then you have to create new box, and for that you have to calculate new P again, and you write new P for prime, say as a new rigging for the added box. So yeah. Yep. So I'm sorry, I don't understand. Yes. Interval of twos. It's a coincidence. It's like integrals of motion of box-ball system. So maybe, for example, you have to write box-ball system. You have like this. If you have such a thing, then actually in this calculation, 0 is 1 and 1 is 2 actually. I'm sorry for the difference of notation. But anyhow, so in this case, at the next time we have this configuration. But actually in this case, if you calculate this, you have 3 and 1 as a partition too. So it depends on the situation. Yes. Yep. Yep. Yes, so in this case, do you mean this case or this case? This one? Yeah. In this case, we have to translate it to this one by increase by 1, like this. In this case, this is a B. No. Actually, this example is not appropriate, so we may add this one. Yeah. Okay, please allow me to go ahead. M is the total number of 2 in the original sequence, B. L is the total number of integers in the sequence. No. Yes, bigger. So we require this condition. This is a number of 2 in the sequence B, and L is the length of the sequence we are calculating. Yeah. So yes, and by using this complicated algorithm, so actually it is only for the case of the rank 1, so it is the simplest case. So we have the algorithm for general n. So in that case, the calculation becomes more and more complicated, but I don't mention that today. So but actually, for now, the algorithm itself is not important for us because only the result is important. So by using this algorithm, we see that the time evolution of box-ball system is linearized in the coordinate of rigging. So to solve BBS, we use this map. So for the infinite BBS, so we fix some big L bigger than 1, so that we can regard a given state of box-ball system like this to satisfy the highest condition. So to calculate a KKR, the sequence B should be in that set. So it is always realized for infinite BBS by adding some empty box. So say 1 to the left. So we choose such a L. So regard a given state, given B of infinite BBS as an element in BLM plus. Then we also have to assume that L is equals or bigger than 2m. And then theorem is as follows. So it was looked by Uniba, Okado, and many other people in 2006. And that when the image of KKR of B is some partition lambda and with length G like this, and some rigging, then, and its time evolution, so I write T infinity for the time evolution rule of box-ball system with infinite capacity carrier. So we consider this time evolution for k times, for example. Then we send this new configuration by using the KKR map. Then this is as follows. So lambda isn't changed, and R is changed to R plus K lambda. So lambda is a constant velocity for this system in the space of riggings, any integer. So especially as we observed, so lambda is integrals of motion. I hope microphone is. So lambda is integrals of motion of BBS. And so so time evolution T lambda is linearized on the space of riggings. This is a result for the infinite box-ball system. And for the periodic box-ball system, we have the similar result as follows. So we fix the period L and fix partition. Now, for simplicity, we assume that there is no same number in partition. So it's this one. We fix this integral of motion for the periodic box-ball system first, and the size of the partition is so M is smaller than, maybe it can be equal, but for safety, I choose this case. Then I define that the set of the sequence of length L such that B is in the set I first defined, and it's not the clear formulation, but integrals of motion of this B is fixed to be lambda. So let's consider this set. So this is nothing but the isolable set of the periodic box-ball system. Then theorem is as follows. It is also proved in 2006. And that, so we define a symmetric matrix A by using the information of P. That one, that P as follows. So this is a G by G matrix. And so Aij is at the diagonal, we have P. So then I and J are equal. We write Pj, and we add 2 minimum of lambda I and lambda j for any ij entry. So by the definition, it is symmetric matrix. And so we define a G-dimensional real torus, JL lambda, by using this A as a period matrix. Like this. Yes. Yes. Do you mean this one? Yes. Yeah. Thank you for your comments. Actually, we just increase the size L depending. So maybe there is some limit only by using KKR map naively. But so we can choose, we can tune L bigger for that case. And so G-dimensional real torus. And oh no. We have the following claims. And the first one is the set BL lambda and the lattice point of G-dimensional real torus J there is a one-to-one correspondence between these two sets. So this correspondence is given by generalizing the KKR map a little bit. Then here, psi tilde, this is the generalized KKR. So because as you asked now, so there is a restriction for R like this, but to calculate this situation, R may take negative or some number, possibly. So this KKR is generalized to include such a thing by introducing a shift operator on the periodic lattice. Then to include non-highest path. Then we have this one-to-one correspondence. Then second, so it is, the second claim is the same, almost the same as the claim for infinite box-ball system. So we have the following commuting diagram. So we have the set of state of the BBS, and it is a time evolution. And we again get some element in this set because this is an isomer set. But on the other hand, we have a generalized KKR map. So we have a point in this D-dimensional real torus. And so, and the time Bluetooth state again gives some point in G-dimensional real torus. And so this is commuting when we define the adding some vector V lambda to a point in this space. So it sends a class of Z on the G-dimensional real torus to Z plus lambda, which is the same as the infinite case. So this is our result for the periodic box-ball system. So because the phase space is finite now, so we rarely have one-to-one correspondence between these two combinatorial objects. And I show an example here. So this is a case that L is 12, and actually lambda is 3,1. And we start with this initial configuration, and its image is calculated as this. Then we go this way, and also we can calculate the image. And so, for example, we see that by adding vector 3,1, we get the next stage. But something different occurs here. So this is the meaning of the generalized KKR. So actually, these two are not highest path, but we can calculate these and this by adding some technique. And actually, on the G-dimensional real torus, this -1,6 is 9.8 because, I've forgotten to write the period matrix A for this case. So it is 10 to 8, sorry, 10 to 10 for this case. And so by adding the vector 10, 2, we get this one. So modulo A, and they are the same point on the torus. So this is what happens here. Then, so this discovery was very exciting for us because KKR is, this map was introduced in a very different context to solve the integrable structure, to study the integrable structure of some quantum integrable system. So to count appropriate, state in the solution. But it can be also used to calculate such a combinatorial thing. And maybe the reason of this success is based on the symmetry of box-ball system, so which is related to crystal-based theory through quantum groups. So maybe there is some good situation this magic occurs. So, and yes, right. That is what I'm talking now. Yeah, yes, right. This is the final goal. So actually, this G-dimensional real torus is the Jacobian variety, tropical Jacobian variety of the spectral curve for discrete KdV equation. So the ring is closed now. So before that, I'd like to mention the solution. So for this periodic case, the solution. So namely, we can write down the inverse map of psi tilde explicitly by using tropical theta function. So let theta z is a tropical theta function introduced by Mihalkin and Zarkov, depending on the period matrix A, like that. So it is a minimum of n times half of an plus b. So this is a piecewise-linear convex object in G-dimensional real space, and this is tropical theta function. So Mihalkin and Zarkov introduced in 2008. Maybe the paper was submitted to archive on 2006 or so on. So in 2006, many interesting results came to me. So yes, you're right. I'm sorry. Yeah, you're right. I'm sorry. Thank you. That is also, but maybe, sorry, let's wait. N is in this space, but Z is in this space. I'm sorry, yeah. Then theorem. So the inverse of psi tilde is given by this function in the following way. So we fix some vectors. So pi, it is nothing but that vector given by, so that p. And so v1 is just one vector. Both are in Z to G. And we fix Z0. This is the initial, the image of initial point related to the initial point. So we consider, we have to say that ut is, so I is from L1 to L. This is a state of the boxable system and written as 0 and 1, but we translate it to the array of 1 and 2. And we use this expression. Then the image of KKR minus half of this P is Z0. Then we define theta Tk as the value of tropical theta function at the O minus KV1 plus T lambda. Then by combining these theta Tk, we can write down the solution minus theta Tk plus theta Tk minus 1 plus theta T minus K minus theta T plus 1 K minus 1. Sorry. Like this. So the detail is not important now, but you see that, so when you detropicalize this situation, you see that U is theta theta over theta theta. So it reminds you usual solution for integral system has this kind of form, tau tau over tau tau. So it has a very similar form. And so we are very happy to have this smart expression of the solution for the periodic box-ball system. And finally, I like to show how tropical spectral curve for the G-dimensional real torus look like. So please recall that in a periodic KDB case, we have some spectral curve as a characteristic polynomial of Lux matrix. So it looks like this one. So this is some polynomial in X, and like this, of this form. And by tropicalizing this one, we obtain the following result. It is already 10 years ago. So we fix the partition, so lambda, like this. And like this, and such that its size is smaller than half of L. And via tropicalization, with this, condition. So it is a conserved integral of motion of periodic box-ball system, and which should be related to the coefficients of this curve. We can calculate explicitly the limit, tropical limit of each coefficient explicitly by using the network description. And we get that tropical spectral curve as this formula. So this y squared becomes 2 times y, and this term becomes y plus minimum of something like minimum of gx plus g minus 1x times cg minus 1 and this is comma minimum of these terms x plus c1 blah 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 and c is 0, And actually, this term reduced to XL and L. Please recall that the variation of delta is 1. Then we have this kind of formula, and each C is given by the summation of some lambda, like A is J plus 1 to G. So we can calculate the limit explicitly. So this is the tropical curve, give tropical curve gamma. Oh, I'm sorry, my time is over, so may I extend 5 minutes? Yeah, sure. I'm sorry for this. Then, okay, I show how period matrix A appears. So the second claim is that J is the tropical Jacobian for this gamma. This is a claim. And finally, I'd like to draw a picture for this curve. This is a linear one. So this is y and x. And we pick up the, border of each terms. And we get the following picture. How it's so we have such a thing like this. Actually, there are no parallel except for this part, but please allow me to do this. This is a tropical spectral curve for this F. Then it includes G cycles, so B1, B2, to BG here. And actually, A is obtained as a, there is a notion of inner product of two paths in the tropical geometry. We can take a product of these two cycles, for example. It gives lattice length of the intermediate, a common edge like this. And we can calculate A as inner product of B tilde K and Bj tilde. And here, B tilde K is a summation of this small b from the left to some point, like this. So, for example, B1 tilde is a summation, summation of all these circles, and B2 tilde is a summation from B1 to BG minus 1, and so on. So now many important problems for box-mode system is solved by using KKR and tropical geometry. So thank you very much for your attention.